Also, can you please speak and not switch off videos? Okay, so this is a point P. Let's say there are 4 lines through it. L1, L2, L3, L4. Then we can write cross ratios in terms of these 3 lines. Just by taking any other line intersecting, you get 4 points and measuring the cross ratio. And this will always be equal. So whenever we are talking about cross ratio, we will assume that it is with lines. Okay. So lines are good for cross ratios. So for example, if you take 4 lines through point and reflect them across an angle, across a line, like if I take some line here and reflect L1, L2, L3, L4 over this, cross ratios will be preserved just because the ratios are preserved, nothing really changed. Does that make sense?
Yes.
Yes, it does.
Yeah.
Okay, great. So this is all for prerequisites. So now we'll actually start with some things. Nope, not this side maybe. Nope, not this side either. This side. There we go. So, so let's say ABC is a triangle. D and E are some points. What we'll do is, for every point on line D, we will take its isogonal conjugate. And then see where it goes. Does that make sense?
We are taking the isogonal conjugates of D and E.
We are taking the isogonal conjugates of every point on DE.
Okay. Fine.
And we are looking at what the figure looks like. Okay.
Yeah.
Okay, so let's say we have some point H. I have not drawn its isogonal conjugate. Just imagine that it exists. So when H approaches BC, where will the isogonal conjugate of H go? What?
A.
A, right? Just because if it's very, very close, the angle, if you reflect, it should get very, very close to A. Right? Intuitively. Does that make sense? Similarly, if it approaches this intersection, then see, because we cannot define isogonal conjugates well for when like our current definition, which is just the angle conditions, does not allow for H to be on AC completely, right? Or does it?
Why does it?
Okay, it can allow just because you can say A is it. Okay, fine. The only issue is essentially that you cannot define it back. Then it's not pairwise well defined. The niceness about isogonal conjugates was that, okay, if the isogonal conjugate, the conjugate of P is Q, then Q is the then Q is the isogonal conjugate of P and P is the isogonal conjugate of Q, which does not make sense when H is on the side.
Be unique.
Exactly. Because then what is the isogonal conjugate of A? So since you don't define it for A, B, and C, you can't define it for the lines. Does that make sense?
Yes.
Okay. But for now we'll pretend that it makes sense to just be like the isogonal conjugate of this goes to A. Yeah. Then similarly here it will go towards B, and when it intersects AB, it will go towards C. Agreed?
Yeah.
Yes.
Okay. Then it can go to some 2 random points because any line can be defined using 2 random points, right?
Yeah.
So now the thing to prove is if we want to show that it forms a conic, then we want to show that for every other point it's fixed. Yeah. Like it goes, like every other point goes to some other point on this conic. That's what we want to show.
Yeah.
So how would we go about showing that?
Maybe maybe like this. Yeah, maybe we can consider the like intersections with the three sides and of any fourth point,
Okay, fix a fourth
and
point.
then yeah, take any fourth point and take the
Okay.
three intersections with the lines, and
Yeah.
then consider the cross ratios of those 4 points. Then once we reflect all of them, the cross ratio should be preserved, right?
Yes, but if that is only on a particular angle, right? So what you're saying is essentially correct. So here I have, I don't know how to take this picture there exactly. Let me see if I can export it for a second. Export image, copy to clipboard. Paste image, perfect. Allow paste. And we have this picture here, right? So we write the cross ratio, for example. We don't need to worry about other points. Let's just say D and E are there and I is there. So the cross ratio AD AI, AE, AH is the same as the cross ratio DIEH. Yes. This is also
Yeah.
DD, DI, DE, DH, and similarly with C. Yeah. This is all DIEH. But then this is also equal to AD dash, wherever essentially wherever D goes, AI dash, AE dash, AH dash. Yeah. Is equal to BD dash, DI dash, DE dash, DH dash. Yes, and similarly with C.
How did you define di dash, d dash, I dash, e dash in
These are
SQL?
just the isogonal conjugates
Oh,
of D, I, E, and H.
Come on, so many isogonal conjugates.
I mean, for every point, right? On the line we are taking it.
The line is absolutely arbitrary, right? No special
Yes.
thing.
Yes, just take any line, fix it, and take isogonal conjugates of every point on that line.
So then we have a hyperbola or something like.
We'll get a conic if that's what you want to prove.
Okay, I see.
See, that's the first thing that we said, right? See, we take any 4 points, D, I, E, H on it. Then AD, AI, AE, AH, the cross ratio is the same as DIEH. This is same for B's and C's. So AD dash, AI dash, AE dash, AH dash is the same cross ratio again. Right? Okay, now if you have 4 fixed points on a circle, right? Then the other points on the circle have the same cross ratio with all of them. You know this, right?
Yes, if they are
Yeah.
some concurrence with each other.
What?
I mean, if 4 points are 4 points and another 4 points have the same cross ratio, I mean, the line joining
No,
them.
that's not what I said. That's not what I said. I said you have this circle. If I pick 4 points on it. A, B, C, D. I fix them. And I vary P on this circle. Then PA, PB, PC, PD is fixed.
Oh yeah, that's true. That's true.
You know this for circles, right? And because
Yes.
circles are the same as conics for cross ratio, this is the same for conics. For any point not on the circle, you don't have the same cross ratio result.
For any point on the circle and any fixed point P and any 4 points, arbitrary 4 points, we have this thing fixed.
No, if I take a point T here, then TA, TB, TC, this is not, these two values are not equal.
Yeah.
Yeah, for some
Any
fixed
point
point,
another on the circle that will be fixed.
Yes. So, and the locus of all points which have the same cross ratio as a particular point on this circle is the circle itself. And because you're only taking perspectivity, this is also a result that is preserved. If you don't understand this, you can take it for granted. Don't worry about it too much. Okay. So that this means that A, B, and C give the same cross ratio with the points D dash, I dash, E dash, H dash. Right?
Yes, but
Yeah.
then by the
Yeah.
lemma you told reflections across angle bisectors. So
Yeah. I mean, this is after reflection across angle bisector. These cross ratios are still equal, is what I said. And does like A, B, C, and D dash, I dash, E dash, H dash lie on the same conic? That means that if you fix like D and E and you vary I and H, you will get that all of them also lie on this conic
I mean,
because the conic is fixed by 5 points.
this fixed thing holds for any conic, right?
Yes.
Right.
Yes. That's what I'm trying to say.
I see. Okay, that's a nice property. Like for any 2 points on a line, we have conjugates, isogonal conjugates lying on a conic.
I mean, for 2 points, it is never surprising just because there's a conic through 5 points.
Yeah.
Like the point is for that entire line, you get a conic always. For every line, you get a conic.
Yeah, that's what I say.
Yeah. Okay. So now let's try to understand what this conic will be. So let's take D and E outside. Right now, it seems to be an ellipse, right?
Yeah.
Like I'll slowly drag D inwards and let's, okay, there's something showing there. And you can see what it behaves like. So it's still an ellipse, 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 ellipse.
is it like when D goes to the interior of circle, something like this?
Right now it's already not an ellipse.
I think when it's tangent the line to the circle.
Yes, so it's tangent, then it still seems like it's not necessarily an ellipse. Okay, now it's inside. Then what is happening? It's a hyperbola now. It's already a hyperbola as soon as you're inside. Some portion of the line is inside. So it seems like if you're inside, if you're intersecting at 2 points, the line is intersecting the circle at 2 points, then it's a hyperbola. 1 point, it's a parabola, and 0 points, it's an ellipse. Right? So 2 questions: why? And the other question is, when is it a circle?
Circle when both points are the vertices of the triangle.
No, like you can't take we discussed this, right? You can't, like the isogonal conjugate of the entire line passing, you can't really define it well.
Yeah.
In that case, you're not talking only, right? When the line is one of the 3 sides.
Okay, yes.
What if we take this line D to be parallel to one of the sides of the triangle?
Then what should happen? You tell me. Does that mean anything? Does that change anything? Because parallelness does not mean anything in projective, the projective world, right?
I mean, like, because when we were defining the conic in the first place, then we just took its intersection with AB and then BC and then AC respectively, and found that ABC all lie on this locus. But if it is parallel, then that may not be.
What?
I meant like when we were actually finding how ABC were lying on this locus of isogonal conjugates. But then
Yes,
what if
that's
the
still okay. That's still okay because you still have the point at infinity along that line.
oh okay.
Also, like for circumcircle, is it just line at infinity?
Yes, precisely. The point is, because you said it now, for any point on the circumcircle, figure out what its isogonal conjugate will be. Let's try to see. So say you obviously have A, B, and C, right? And you have some point P here. Okay, I want this one to be visible, let's say P. Some other visible color. Let's say this. Then angles P, A, B is equal to angle Q. Q is, let's say, the isogonal conjugate of Q, right? Q what?
Yeah.
QAC. Yeah,
QS.
is that correct?
Yeah.
Not
Technically,
quite. You have,
CIQ?
yes, good. Because you're trying to figure these things out very carefully. Just make sure your angles are in the correct order always. It becomes a point at infinity, not the point at infinity, because we have not fixed the line. So it's just a point at infinity. But you're right. PAB is equal to CAQ, and similarly, let's say PBA is equal to angle come on CB. CBQ. So now it goes, let's see, you had this line, it goes somewhere like this. So Q is somewhere along this line, which is the reflection here. But also angle, let's say QAB only. EAC is equal to QAB, for example. PAC will be, yeah, PAC is BAQ. So now, as people are claiming, we want to show that Q is a point at infinity. What does that need? Then we want angle BAQ, this angle, plus angle QBA. So then we should change it to QBA again.
That should be 180 degrees.
That should be 180 degrees. So angle QBA is what?
CBP.
CBP. So if you just check the correct order, this is just the cyclic property, the 180 degrees. Yeah.
Yeah.
Good. So we get that any point on the circle goes to a point at infinity.
I think I have another proof.
For a point on the circle going to a point at infinity.
Yeah,
Okay,
yeah.
go on.
because it
Is it
has to
just
be
like
the
a? Yeah, sorry, go on.
it has to be the circumcenter of the reflected points, right? But the reflected points just are collinear by some sunlight.
Sure, that's a very good argument. Yes. Does everyone see that?
Yes.
Very good. That also works. So we get that every point on the circle goes to a point at infinity. So well, if the line intersects as here at 2 points in the circle, then you should have 2 points going to infinity, right?
Yeah, so it can't be any
So it has to be a hyperbola.
hyperbola. Yeah.
Yeah.
Now, if it does not intersect at all, then there are no points at infinity.
Wait,
So it's an LS.
doesn't parabola also have 2 points at infinity?
No, a parabola has 1 point at infinity.
Doesn't like a parabola has 2 arms.
Yeah, but okay. So let's do this. X squared, right? Let's draw that. That's the simplest parabola you all know. So let's say there are 2 points at infinity on it, right? Or let's say any point at infinity along it. So through O, let's say, or through this point on the parabola, there is a line passing through that point and the point at infinity.
Yeah.
Okay. So for any, let's say it is a line at angle some theta, right?
Theta
it-
2?
So for some angle, let's say it's some line, right, like this, right?
Yeah.
But how many, what lines are there that do not like are eventually not outside the parabola in some other direction?
Oh, there's just one.
There's just one, right? This.
The symmetric, yeah.
Yes. The only point at infinity along the parabola is along the axis.
Okay.
Even though it does not seem to, because you might argue that it keeps going far away from that point, but that's the way it is.
Thanks.
Make sense?
Yeah.
Okay. So, and in case the line is tangent, we have a parabola. With me so far?
Yes.
Okay, great. So now let's look at some interesting cases. The first interesting case that I'll mostly focus on, or why this class is on hyperbolas, is when one of the line passes through the circumcenter. So I'll just change this to O.
Oh, when the line passes to the circumcenter, we might have some special properties, right?
Yes, so that's what we'll explore. Is my net breaking? Sorry.
It's fine.
Okay, great. So we'll focus on this
Wait.
case.
I see two high. Oh no, it's okay. Nothing.
Yeah, it's a hyperbola. It has two directions. Okay, so let's see.
I
So
mean, I
what?
was just asking that the second curve which we are getting, does the second curve intersection of the second curve and the circle has something special? I mean, is something special?
I mean, it's interesting to call it a second curve, in the sense it's just one curve.
No,
But
I know
yes.
it's one curve. I mean, the other direction intersection of the circle.
I know what you're saying. Just say, so the correct way to say it is the intersection of the hyperbola with the circle, because it is just one curve, is all I'm trying to tell you.
That's just isogonal conjugate of point at infinity along the line.
Yes, good. Along what line?
Whatever line you're taking conjugate of.
Good. We'll get back to that. So let's try to understand where the nice thing firstly we have is, for what angle reasons. One, it's a line passing through O, so what will the isogonal conjugate have?
Orthocenter.
Orthocenter.
Good, orthocenter. So the orthocenter will lie on the hyperbola. And the other nice thing that we can understand from the circumcenter is the 2 points at infinity at the isogonal conjugates of diametrically opposite points. Right?
Yeah.
Yes.
So if the points at infinity along the hyperbola are x1 and x2, then what is the angle x1a, x2?
$180.
So, what?
Sorry, I misunderstood.
No, it's okay. It's okay. See, the lines have exactly 1 point at infinity. So this side and this side are the same when you're talking about points at infinity. See, so let me draw as.
Can you repeat the question?
Okay, so if the x1 and x2 are the points at infinity, what is angle x1a, x2?
Okay.
X1, X2 are 2 points at infinity.
Are the points at infinity along the hyperbola?
I see.
The hyperbola has 2 points at infinity, right?
The angle is 90.
The angle is 90. So the points at infinity along these 2 lines that I just drew, along this line and along this line. So it's clearly 90 just because x1a, x2 is equal to jak because of isogonal conjugates, this reflection
Okay.
across the angle bisector.
X1, X2 is equals to
And angle xay, let's say x and y are the isogonal conjugates, is equal to angle jak, just because x is the reflection, line xa is the reflection of line ja over the angle bisector. Line ay is a reflection of line ak over the angle bisector. Because at the points of infinity were the isogonal conjugates of the intersections with the circle, right?
Yes.
So the angle of the asymptotes is 90 degree, is the point. Angle xay becomes 90. So if you take the line, the asymptotes, they intersect at angle of 90 degree. Here. Does that make sense?
Yes. So there, it's a rectangular.
Yes.
Uh,
Yes. So these are rectangular hyperbolas just because they intersect, the asymptotes intersect at 90 degrees. And you can argue the same thing in reverse. If like the points, like the asymptotes were perpendicular, let's say, then the angle xay will be 90. So the points should be diametrically opposite. So the line should pass through. So it should lie on the hyperbola. Does that make sense? Foundation. Okay. Does everyone understand the structure?
Yeah.
Okay, so we'll try to explore some properties of these. Okay, so one thing is, as everybody said, we should see how nice this point is, right? The 4th intersection. Yes. So now if I add in let's say, the orthocenter also of BLC and ABC. Okay. So ABC is your triangle, the one you started with. H is here. D is here. Okay. The conic our hyperbola is ABCHD. So since it's a rectangular hyperbola, it also passes through the orthocenter of BCD. Right? Which is some H prime. Agreed?
The center of BCD.
Yes, because it's a rectangular hyperbola passing through BC and D. We just showed that rectangular hyperbolas passing through ABC pass through A. Right?
It's just
Yes.
taking the isogonal conjugate of O with respect to BTC.
Yes, exactly. Not completely, but yes, because the line that you're taking the isogonal conjugate of to get the same hyperbola with respect to BDC and ABC are different.
Right.
But yes, that's the spirit. So it gets some H dash, right? So now AHD, you know that AH is equal to DH dash. This you all must know.
Yes. 2R cos.
2R cos A, right? And
Yeah.
A is fixed, so the length is fixed. And they're also parallel. So this is a parallelogram.
How is D defined again?
D is the intersection of the conic with
Okay.
ABCH.
Yeah.
Or you can take it like D is the isogonal conjugate of the point at infinity along the line. Right?
Yeah.
So AHDH dash is a parallelogram on the hyperbola. What does this mean? If you have a parallelogram on a conic. So let's see the structure. I shall endeavor to create orthocenter.
The common midpoint is center.
Yes, good. So parallelograms can only happen on conics when there are reflections across the center of the conic. Good. This is one. Oh yeah, I already have this. Great. And the center BCL. Not triangle center. M. So our figure is like parallelogram is AG. Yeah. And I'm trying to mark this line. Okay. So now what Atul was saying was that if you take this midpoint of AM, it seems to be the center of the hyperbola. So what you can prove is, this I'll leave for you to prove, I'll not prove now, that if you have a parallelogram on a conic, the center of the conic is the midpoint, is the midpoint of the, is the center of the parallelogram, or like the midpoint of the diagonal, either diagonal of the parallelogram. Okay. Is that result okay to digest for everyone?
Yeah, sure.
Okay. Can you all believe me for that? Okay, great. So now let's proceed. So one thing this tells you that if you look in terms of ABC triangle, and G, then the center of the hyperbola is the midpoint of GL, right?
What was G again?
G is the orthocenter. I'll just rename it for confusion removing purposes.
What center of ABC?
Orthocenter of ABC, yes.
That's why it lies on 9 points. So that's fine.
Yes, so the center lies on the 9-point circle because you're taking half homothety of a point on the circle from H.
Oh, yeah.
So the center of the hyperbola will lie on the 9-point circle. Does everyone understand that?
Yeah.
Yes.
But that means, see, this is a rectangular hyperbola. ABC are arbitrary essentially on it. And you have this special point N, which is just with respect to A, B, C, H, and P. That is the center of this hyperbola. So what you can in fact do is take four arbitrary points on the plane, A, B, C, D, and take all the 4 9-point circles.
Yeah.
They will concur just because they should. That point will lie on the that the concurrence point will be the center of the hyperbola passing through A, B, C, D, and H, where
Oh,
H is
yeah.
also center of ABC. If you take the orthocenter of ABC, which is H, ABC, H, D, take that hyperbola, take its center. That lies on all 4 9-point circles, right?
Yes.
So you get that concurrence which you had to angle chase.
Yes, this is the fancy solution.
So you can prove more cool things. You can prove that, okay, if you take so how did we start? Take some point, let's say P. These I'll leave for you to prove. I'll not prove them. So let's take some point. I'll rename it in a second. I'll delete the asymptotes. Is that okay? I think they're just messing up the figure at this point. We don't really need them. And even M I'll remove for now. Okay. What is G even? Okay. So point of the hyperbola would say here, this is P. Yeah, point P. Why is there always a G coming up? Am I doing something wrong? Okay, P. Let's move P inside. And do you mind if I hide this line that we started with? I don't think we need it right now.
Yeah.
Okay, great. Finally, we have a semi-clean figure.
Also, you can remove K and J.
Great. K, J, F. Is that needed? What is F even? I forgot. Oh, it's the isogonal conjugate of D. So yeah, so EFP, let's try to maybe take AP, BP, CP. Also, we need midpoint of L and H. That's the center, right? So center E. Conic E. Okay.
Like N.
Yeah, I'll rename it to N. Okay. So this point, and you take this one, and so observe that it passes through the okay, what is P being annoying? Okay. So the point is it intersects here. This point.
Oh,
So if you take the Sevian triangle and take its circumcircle, it passes through this Ponsonby point in the center of the hyperbola, which we call the Ponsonby point. So you can take any point on the hyperbola, take its Sevian circle, it will pass through this point. In fact, take
its
any
what circle?
Sevian circle, I'm calling it, just because you draw the Sevians, take the intersection point.
Yes.
And you can even take the foot of feet of perpendiculars onto the three sides, make that circle, that will also pass through this point.
Yeah, any three sequence would do, right? Which concur.
I mean, on the hyperbola.
Okay, yeah.
So these are some nice results. So you can try proving some other things and you can look at some handout. But I'll show you. Okay, is something going on in the chat? I have not checked it for a while. But okay, we can look at some interesting configurations now, I guess. One configuration we can look at is when right, okay, I'll define I is the this is interesting because the isogonal conjugate of I is I itself.
Yeah.
So it's an
Yes.
interesting thing to think about how it behaves. So I'll just create it in a second. And we will change this conic definition from F to I. Yeah. So you have this conic now. This is called the Feurbach hyperbola. Okay.
Okay.
So this is the isogonal conjugate of what line?
OI.
OI, good. So now, but observe that I should do something so that, okay, this is what happened now. Okay. Let's remove P for now. It's not relevant for now. We'll add it later. Okay, great. P is gone. So we have this hyperbola now. So what is it the isogonal conjugate of?
OI. OI. Yeah.
OI, good. So can OI intersect this hyperbola at any other point?
No.
It definitely intersects
No,
at I.
because
Sorry, go on.
no, because it can't. Because if it does, then the isogonal conjugate of that point will be itself as well.
Exactly. Then the isogonal conjugate of that point should be itself, which it is clearly not.
Yeah.
So that means OI is in fact tangent here.
Yeah.
Okay, that's the first result that we see. Now this center here of this hyperbola is called the Feurbach center. You might have heard of it. Or like the Feurbach point of triangle ABC. So can you try to see why the incircle and the incircle of triangle ABC? So this circle, center and radius I. This point, circle and
Which point is the Feurbach point again?
the center of the Feurbach hyperbola. It's 0.5.
It's, I guess, D 0.5.
Yeah. Thanks. And why did the polygon go away? Did I unselect that? Oh my god, what is happening? Ah, I see. The delete option was selected. It's okay, we are back in the business. Okay, yes. Good. Oh, the center went away. Great.
Just try and circle.
Yeah, I mean, we need n as well anyway.
You can just define n as in circle intersection.
No, I want it to be still there for general points when we move later away from this structure. So n is clearly on the 9-point circle from what we have discussed. But what is being claimed here is it's also on the inner circle. Is that clear why it should be on the inner circle?
You told that if you drop feet, that circle also goes through.
Exactly. So if you drop feet, that circle also goes through. So it is also definitely on the inner circle. But now why are these tangent?
Oh, wait, we just proved that. So the 9-point center is okay. 9-point center is the midpoint of HO,
Yes, 9-point center is midpoint of HO.
and the in center. Okay, never mind, anything.
So it
Okay.
suffices to show that N9, I, and N are collinear.
Sure.
Or maybe we could try to show that if both the circles intersected at another point, then that point would also be the center of the hyperbolas.
Sure. How do you do that?
Right.
That's a good idea. It's a good idea. How do you do that though?
Wait, how did we get that analyzed on the encircle again?
I told you that if you take any point in the hyperbola, drop the feet on the three sides and take the circle, it will pass through the center.
All right.
This is also angle chaseable though, this result. This is something you can try to angle chase. Okay, this is something I'll leave for you to think about. Another thing that you can like, so you can think of other points that lie on line OI. They will also behave well with this hyperbola. You can also think of, let's say, line OH. That is interesting because then they are isogonal conjugates of each other. So it actually becomes or the figure actually becomes ABCHO, the conic. And OH, you also know that, okay, the center lies on it, the 9-point center lies on it. So their isogonal conjugates will also lie on this hyperbola. And many interesting points. You can think about these things. I think I can show you some other results, or we can actually try some recent problem. What would you prefer? Problem. Okay. Okay, great. So this is this year. So we'll do the following problem, which is this year's USA TSC T9. Atul, correct me if I'm wrong. Is he here?
Oh, he's not here, but yeah, I think it's P9.
Okay. How much time do I have actually?
17 minutes.
Okay, and then it might not be right. Okay, let's do this year's ISL then.
Oh, are you going to do the G6 one?
Yes.
Dead. Okay, no problem. Well, I just asking that, is there any solution not using hyperbolas of G6?
There is, but then it's not, it's not nearly as motivated. Hyperbolas are just like obvious here, if you know what hyperbolas are.
Yeah.
Like, I'll
So we
show
can-
you why.
I mean, can we just have some synthetic finishes on this problem? Or like,
It is like, come on, what is about hyperbola that is not synthetic enough for you?
I think it just went without conics.
Without?
I think it just went without conics.
Okay, fair enough. There are proofs, but I don't, and the complete finishes, like solutions that never talk about conics at all. I'm saying that is there, but like it's not nearly as motivated. So you had the perpendicular line. Can anybody tell me the statement? I'll draw it. You want angle bisectors of, tell me if I'm wrong, DBC and DCB to concur on this line, right? Not on H, yes. Okay, so you want to look at point P such that the angle bisectors here meet on AH, which is somehow the foot of the altitude is called AH, which is the most absurd thing ever. Actually, it's not exactly called, but fair enough. These angle bisectors here intersect here at these points. You have this line, you have this intersection, right? So now what the problem statement is that BH passes through a fixed point if the, for like all
Can
D
you-
such that angle bisectors of DBC and DCB concur on AE. Sorry.
Can you
can you-
explain the problem?
Yes. So ABC is a triangle. AE is the altitude.
Okay.
Consider all points D such that the angle bisector of DBC and DCB concur on like intersect on AE on the altitude.
D is a
Okay.
moving point.
D is a moving point. Yes.
Okay.
So now let the angle bisectors also intersect the other sides at F and G. Then FG intersects the altitude at H. Prove that DH passes through a fixed point.
Okay. got-
So all this is scam for saying that the incenter of DBC lies on the altitude, right?
Yes.
And DB minus BC, that means is equal to BE minus EC.
Wait, what?
Yes.
Just because if you have a triangle and you have its in touch point on the side, the difference between these two lengths is the difference between the lengths. This is S minus B, S minus C,
Oh,
this
yeah,
is B and C,
Yes.
right? So this is literally just the hyperbola with foci at B and C passing through E. D is just a point on that hyperbola. There's nothing more to it. Does that make sense?
Yeah.
So D comma C comma E. There we go. So we will tether point D to this hyperbola D to the point D. Okay, where are brackets? There we go. Okay. Is the problem statement clear? So as D is varying, prove that line DH passes through a fixed point. So I'll show trace. It seems to be passing through a fixed point where?
It
On the
intersects the
hyperbola.
parabola. Hyperbola.
On the hyperbola.
Okay, good. This is something you have to kind of guess. Okay, but this is not insane to guess. They have to try some cases and I think it becomes somewhat clear. I'll stop.
You can try
here.
incenter
I
at A and
guess-
incenter at infinity. It forces it to become this A cap abuse.
You can try what?
Like taking the incenter to be A and then incenter to be infinity.
Okay. So they're suggesting take incenter to be A and incenter to be infinity. You'll understand where like incenter is infinity along AE. Then this actually tells you what the point is, and the lines are very clean in those cases. Does that make sense?
Yes.
Okay. So now let's have this point here. And we want to claim that as D varies, yeah,
We get a parallelogram, something like that.
where?
No. Sorry.
No, it's okay. So now, what else do we have here? The incenter is here, right? So these are the foci, B and C. So then there is this nice thing that, again, I want you to try to prove, or you can read Franz's article, that if you have point D, if you have a point D on the hyperbola and B and C are the foci, then the angle bisector of BDC passes through is the tangent at D. The tangent at D is the angle bisector of BDC. Does that make sense?
Yes.
You take the
Wait,
foci. You take the foci, you take a point on the hyperbola, you take the angle bisector. That will be tangent to the hyperbola. This you can prove. Or you can read Franz's article. Okay.
Okay.
But the angle bisector passes through the in-center, right? That we know. So this point is also a very clean point, J. Yes? Okay, and in Atul's case, where A is the in-center, then what is happening? Where is D?
D goes to that fixed point.
D goes to that fixed point. But what would that mean?
That is tangent.
That dA is tangent to the hyperbola. So that fixed point in fact should be the point at which A is tangent to the hyperbola, right? Like, so if you take tangent from A, honestly, I know that I'm just telling the solution at this point instead of motivating it, but sorry for the time constraints. Oh, sorry, it's due to the time constraints. Now, the only thing to observe is that the isogonal conjugates of D, sorry, the tangents from D and E to the hyperbola meet at J. Yes? If you take anything through any line through D and any line through J and let it intersect the hyperbola, that will give you cross ratio 1, -1.
Can you repeat?
So if you have some line through J, yeah, and you take this point wherever it intersects the hyperbola. My God, what is the hyperbola? Sorry, I know I've lost a lot of you at this point. Now cross ratio of DEKI is -1, just because KI passes through the point at which tangents at D and E meet. This is again from your circle thing. Circle, you know that the tangents meet on the symmetrian, right?
Yes.
It's the same thing. So you can you instantly have DEKI has ratio -1, and you can just now project it through H onto the circle, and you'll onto line AE and back on, and from J on back onto the hyperbola, and you get your result. I think I'm not helping you too much now, so I think I should stop here. And it's close to time. You can try finishing it from here. I think I've given a lot of it away.
Hey, also, can you provide some, I mean, resources, some articles if it's relevant
Yeah,
for
actually.
class?
Yeah, sorry for this. I think it became a lot more chaotic and not nice than I
No,
would have desired.
I found it quite nice and interesting. That's why I wanted to read something.
And also, like Archie has a handout. You can find his website and link.
Yeah, you don't know. That handout is also somewhat old-ish. You can read that perhaps also. I think if you are looking to just understand, for example, the angle bisector result,
I link
you,
Pranjal's blog also.
yes, so you can look at Pranjal's blog. He has some nice posts there. And it's interesting. Also, just like what I want more than anything with understanding conics is you should understand that it's essentially the same as circles, just looking from a different place. Does that make sense?
Yeah.
Yes.
So all the projective results, like for example, the cross ratio -1, just when you intersect the tangents and you have that line, those are preserved. Or whatever nice results that you imagine, which are projective, stay.
And that's the whole point behind projective transformation.
Exactly. Projective transformations or whatever you read are essentially just these basic transformations that preserve these nice things. So one thing is just this visual thing that I'm trying to tell you. There is this thing called, one other thing that you can do is this thing called shearing. Just like you have your lines, the axes are padded like this, right? Just change your axes like this, and everything will have a natural change. And still things get preserved.
Oh,
If you want to read some, I mean, okay, if you actually genuinely want to learn about conics and all this and some basic stuff, you should just pick up a Copian's book.
which book?
A Copian. I'm sure Atul has already prepared the link or something.
Oh, you want to send a copy?
I'll just send you the link on chat. It's okay.
No, I will
Geometry
be
of
faster. Yes. that will be
how,
fun.
like how are you faster?
Done.
Like, yeah, so Geometry of Conics by Akopian. That book also you can look. That is a very good book. Some nice things. Anyway, don't worry. This is supposed to be supplementary for fun's sake. Just because some recent problems have used it as like, yes, I can pretend that they are useful.
Also, like the last problem, the ISL one, like if you know, we knew the part of like taking the conics, like how hard is the problem?
I think one main thing is just guessing the point at which the concurrence happens. That, for example, is done well by, as Atul said, when you actually just take
Yes, the
just two
incentive.
A as the in center and some other cases when you realize. And I think if you know what a hyperbola is, you know that this is a locus of D, which is just good as like a picture. But even if you don't have that, it's simple to realize like most angle conditions that you will have, oh, these angles are equal or this concurrence happens is in some sense degree 2 condition. And degree 2 curves are conics.
Yes.
Like whatever degree 2 means to you. Like I don't want to expand on it too much. Yeah. Anyway, this is supposed to be fun supplementary thing. I used a lot of stuff that I think they have not introduced yet. For example, cross ratios or things like that. Yeah.
Do I stop the recording?
Sure.